Hi everyone. Previously, we finished the simulation of the advanced model, and while we were simulating, it was diverging, and then we used the for the solution we gave the controls and decreased the momentum to zero point 0.3 and had to go to the advanced controls where we gave the BCG step for energy and electric potential. Now, in today's session, we will continue the same solution for doing the parametric analysis. And for that, we finished the current voltage. We had these, we plot all these report plots, and we had the report file, but today we will overwrite it. And in this session, we will go towards the parametric analysis. And for the parametric analysis, we'll do by changing the load conditions on the fuel cell and then giving an adequate number of iterations so that the solution can converge at every load step. For this reason, we will go towards the user defined not automatic control. So we'll go towards the automatic control of initializing and modify the case. So we want to modify the case for each iteration, for each step. Now let's check this, and we'll directly start by by starting it. And all the things have been defined in the guidebook as well. So in the guidebook, it is easy to follow the guidebook, but sorry, it is you can read the guidebook, but there are a lot many complications involved. So the video will cover most of the complications that are not described, or it is very difficult to describe by writing them down. So this video will contain all the details for doing that. Now, and to give the initial boundary condition, what we need to do is for we actually need to modify for each step the SOFC model. And as you can see right now, we converged it to these parameters. Initially we converged the system to total system current with an under relaxation factor of 0.3. Now for the initial or the original setting, we need to create a macro that can configure the same conditions. So let me define that the macro can be made by GUI, graphical user interface, or by using the text commands. So let's start making the macro for the original setting. So we go to edit, and the original setting we will mark it edit and define a macro for the original setting. So we can say it macro initial. Let's call it macro initial. So that is, it is giving the initial setting, and we give OK. And now you see that saving input to macro initial. The macro name is macro initial, and we will, by doing with the GUI, we can set it by 0.3, enter, and that's not gonna, yeah, this is the original condition, so give it 0.01, enter, and apply. Okay, and end macro. So we did define the macro. We did define the macro, but to check whether the macro is actually working or not, so let's give it, hit enter, and we'll write in macro initial, and you see that it runs, but there was to make sure that there was some change done in it. So let's go and type in 0.2 and convert it to any system voltage, let's say 1.1. okay, we set it manually, and then say let's check that whether it is working or not. So okay, let's check whether the changes were made or not, but you see that it hasn't made the change. So by using the GUI, it is really difficult to grasp that if whether the changes will be made or not. So it is always preferred that we should avoid using the GUI for creating the macro, but go instead go towards the text commands. And okay, now let's modify the macro. So, and here I would like to introduce The next important thing is the text commands. So we have the Ansys Fluent text commands list. This is already from the Ansys website also. This is available over there and updated for all the versions. So here we have the fuel cell text commands, and specifically for the solid oxide fuel cell with unresolved electrolyte. So here what we want to use is model enable, and this is we want to change. We want within the parameters, we want to change the parameters. So now we will modify the macro using the text commands to modify the model parameters. And so we'll go to define macro and we'll just define the macro initial again. So if you select this one and OK, macro initial already is yes, okay. Now it is saving input to macro initial, and instead of going to the GUI, we'll direct go towards the text commands and give the command define models SOFC and model parameters. We can give directly model parameters, and here enable electrolyte conductivity model. Yes, make sure that the only changes we need to do are the specified system voltage, no, and total system ampere current 0.01. Enter. There is no leakage density, and the current under relaxation factor is 0.3. Okay, enter. The rest of the things are all the same, and we said we'll do end macro. Now macro initial is defined. So now if you go here, all the changes are made. 0.3 and 0.01 is the system ampere current. So now let's change it to, for example, 0.7 and convert it to system specified voltage. Apply. Okay, and now we will run the macro initial. Okay, now the macro initial has been executed, and let's go here and see. Now it's being set. So the macro initial, when we define the macro using the text commands, it's more reliable. So it's better that we use the macro initial, the macros, we make the macros using text commands. We can use the GUI also, but again, reliability is very important, so we will prefer using the text commands. So okay, and now here we define. So in the original settings, we want that it should again continue for at least 50 iterations, and the reason is that we want to get the animations and the contour plots, etc. And we will define macro initial in the text commands. So okay, and now we have, if you click on the original setting, so we have defined it to be macro initial, and it will run 50 iterations on the original settings. Now we want a new set of modification where we will change the specify the system voltage. So we'll go to the new and mark it as modification 1, and okay, we'll give 50 iterations again, and we'll define a macro, and here we will, let's say, give it a voltage of 1 volt, because at the initial setting it will take about, it will be almost 1.1 volt or something. So we will start from macro, we can name it V 1.0. So we named it macro voltage 1.0. okay, and now it has saving input to macro 1.0. define models SOFC model and model parameters. Convert to specific system voltage, yes, system volt 1.0, and current and relaxation factor, we don't want to change it, and now end macro. So we have defined the macro for the voltage of 1.1, and we can define all the macros over here. So we can just define macro 0.9, macro 0.8, 0.7, 0.5, 0.4, and then we want to get the finalized solution again at back at 0.7. So we'll make all these macros. Okay, define macro v 0.9. okay, saving input. So define models as model parameters again. System voltage is 0.9 and end macro. Okay, now again define macro for 0.8 volt. Okay, and here we want to give define models again. And here we will give 0.8 and macro. Again we will define the macro over here for 0.7 and end macro. We'll define the macro for 0.6 and macro. Now again define the macro for 0.5 sorry and macro. And the last one we want to define is at 0.4 and macro. Now these are all the macros that we want to add over here. So this is the modification one, and here we will add the macro v 1.0. so okay, unselect it and select this one, macro at 1 volt, new modification to 50 and macro 0.9. okay, new you can copy it, just change the names, Control C and okay, new 50. okay, I think we missed, this is 0.8, this should be edit, this should be 0.7. okay, and this is 0.6. so we have initial setting, macro initial, macro 1, 9, 0.9, 0.8, 0.7, 0.6, no, 0.5 and 0.4, new 0.5. Okay, new 0.4. Okay, and in the last we want all the systems to be back at 0.7, so we'll add new and we'll go back at 0.7. Okay, so now we have defined all the macros, so we can have macro initial 1 volt, 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, and then finally 0.7 back again. So now we have set all the cases where which we want to solve for our automatically modification of cases, but we want that at every time step we should have the contour plots. So this is the time when we want to define all the contour plots. So let's go and make all the contour plots first. So we'll define a new contour plot and we want it to be auto range, and first thing is temperature, so we'll name it temperature, and plus this is an auto range and this is local temperature, so we'll make it local for this time step, and temperature, static temperature, and we mainly want it only at the electrolyte, but there's no cathode. So and for the temperature it is okay that we can have only electrolyte or and the anode or cathode, that will be the same temperature. But when we go for making the molar fractions of H2 and H2O, then we definitely need one electrolyte anode side, so it is better that we make a zone for one electrolyte anode. So for making the zone we can go to domain, surfaces, create zone, and we will make a create for one electrolyte cathode, create, but it renames it, so we can rename it, go to manage, and we can call it wall electrolyte cathode, wall electrolyte cathode, rename. So now this is wall electrolyte cathode, we made the zone, so it should be visible over here. So now yeah, we can, for the time being we can have anode also, that's no problem. And we want to draw the mesh edges with only outline of, we don't want the walls, we only want the inlets and outlets to be available. And display, these are the walls right now, so we should turn off the grid. And I think for okay, but we don't want the shadows right now or the reflection. And transparency we want to increase up to 80%. And now display, set it in the form that we would really appreciate, exponential float, because we will save that state, and then that all the figures we will have. We can directly have it in this direction also, so this is also applicable where this is, but we should be really sure about it. I think I don't like this, so both the inlets should be, I would prefer it like this. Here's the fuel side and here's the oxygen side. Or no. Now you can set the views also, so you directly views, isometric bottom, top. I think I want to rotate it. If you place it in the top orientation now, this in the positive z direction is actually the oxygen fuel or the air flow rate, and in the positive x direction is fuel flow rate. So I would prefer that the fuel flow rate should be in this direction, so you can have, yeah, this is better, that fuel flow rate is in the positive x direction. This is the fuel flow rate and this is the air flow rate. I was actually looking at something, and we can go for isometric also. So I think isometric is better, so let's stick to isometric, and we should make some changes. We can also have the like we should properly resize and everything at this stage, because we will save the state. Close. And in the mesh we can maybe have gas channel outline for, we can have it in the display that we should display the wall channel anode and wall channel cathode. But if we are looking for an isometric view, this wouldn't go low, because if we said okay and display it, now it is a little bit overlapping on the edges and it makes a confused image. But if we were looking at the top surface, now it was really good, it defines properly. So if you go to the views and select the top, apply, it looks good, but while defining all the inlet and outlet. But we are better with the isometric, apply, and we can adjust it according to ourselves for better contouring. Okay, but in that case we should actually not, for the draw mesh option, and this is okay. So okay, so once we finalize this image and also the contour lines, yeah, it looks fine, it looks really nice. Now with this temperature, the local lights temperature, we can get this image and we will save the state over here. So use active. Now we save the state, display, and this is our first animation plot that we will make. Now the next is we want to make the when we want to make the animation for changing the load conditions. Now we want to have the temperature range that should be able to accommodate all the increasing temperatures that we will get at the highest load condition. So for the highest load condition, we have already done a few things. So we'll go to temperature local, and at this condition, before going to the final analysis, so I've already done the few analysis at all the conditions. So we went up to a highway, the highest temperature of almost 1580 degrees Celsius, degree Kelvin. So here now we should make a contour for global range, copy, from 1023 to, that was 1580. Now in this it is completely blue, but it will keep changing like when we apply more load. So now we have temperature local and sorry, we can name it GBL for global and LCL for local, and okay. Now we plot two temperatures, local and global, and now we want to make the control plots for hydrogen and oxygen. So we will make new control plots for H2 mole fraction local, and we'll range it as species mole fraction of H2, and select all and only at the wall electrolyte anode side. Again float, and we want to have control lines. Draw the mesh. Okay, now this is it for the animation purposes. And we want to make a global range also. For the global, again, we need to go to the lowest hydrogen that will be there. 0.97 is the maximum, so we want to have a local one also, and the minimum most goes to 0.36, so we'll give it a range of 0.35. Three five. Yes, okay, close. Now we made two uh, temperature and hydrogen, and the last one we have oxygen. Just for demonstration, we can have many others: nurse potential, water production, and many other controls, but right now this is just for demonstration, so we're only working with species, temperature and species. So let's make new, and this will be O2 mole fraction at local conditions. So we will auto range it, select none, and in this time we will definitely need the cathode side and safe display. Sorry, not mole concentration, mole fraction of O2. Yes, this should be floating, and we should add control lines and also draw the mesh. Now you see we have a very good representation of the oxygen mole fraction, and here you can see it's all is at 0.21, but the localized conditions for O2 we have them, the minimum most mole fraction went up to 0.08, so we should color the mole fraction up to 0.08 for the global conditions. So save display and copy it. So this will be O2 mole fraction in global condition. Global condition, and you don't want to auto range, so minimum will be 0.08, as you can see here. So it was 0.08 up to 0.21. right now this is at the maximum conditions. So we have made the contour plots also, and but we want them to be saved at every final at the final iteration of every time step. So to do that we need to have the execute commands, or we can directly make the animation. Making the animation is much easier compared to making the execute commands. For the execute commands we again need to make the macro for saving it, but there will be a difference in the animations and the execute command. So we can directly make create animation solution animations, and for the animations we can have, for example, temperature local, and record every 50 iterations as a jpg image, and we want to make select temperature local. So we got a new animation. So we here, if you go to solution animations, we have temperature local, and these are all the modifications we gave, and we have temperature animations. So we'll add them for all the animations, like create solution animations and temperature global every 50 iterations. We want to save it as a jpg image, and sorry, and temperature global. Okay, now we have two animations. So create solution animations h2 more local, h2 more fraction as local at every 50 iterations as jpeg image. Okay, and again I want h2 mole fraction and global. Save as jpg image. Okay, now finally for o2 also. Now we have the solution animations, but it is better to make an execute command so we can see the difference. What will be the difference between we make from execute command and from the solution animation? So let's make a copy of the temperature for a local and global conditions. So we'll have a create edit, and here we need to again make the macro. So let's make a macro and name it command one. Is for command one we can say like we want to display the temperature contours properly with so temp display. We want to, let's make it contour temp local, and in order, but we can't directly define the command, so repeatedly after every 50 iterations, and we will define a macro, and for the macro we will name it macro temp local. So okay, macro temperature local, and keep in mind that we are displaying it over here. So now we will use the GUI to set the display. Okay, so okay, and now it is saving input to the macro temperature local. So we will go and select from here from the menu every time when we are making the macro. Make sure that we start selecting from the outline view, and we'll go to temperature local, and display it. Draw mesh, play, close, and static temperature, display. Close, and here we end the macro. So now this macro has actually saved the display of the local temperature, and I just want to copy the name, and here we give the same command, macro temperature local. Okay, now we define this command. If you see in the execute commands, now we have made a command, but right after this command we need the next command to save it, actually to save the picture. So is this active? So if we make it, and this is active, yes, and the next command is new save pic, and execute every 50 iterations. And we don't want to we don't need to define the macro for this. This is a simple command, so we can directly say display save picture, or we can in the GUI or in the guidebook it is also mentioned. The command is mentioned in the guidebook. Before giving the command directly here, so we can actually check whether the command is working or not, so we can write define, sorry, not define, display and actually we should give the command like this, display save picture and temp 001, let's say temp local 001 dot jpg. Okay, now where is this actually save? It is it should be saved in the for root folder. So if you go to the root folder, in my case it is Fluent, the first Fluent case, and yes, this picture is saved properly. So this is now we are sure that this is saving the picture properly. But if we give the same name, it will give a different it will keep overwriting it. So we need to have different according to the iteration number. So we should give the same, like, copy this command and give directly as a command over here, display save picture temperature local, temperature local, and we'll add a percentage I. Percentage I will add the iteration number dot jpg. Okay, now we have two commands. First will display the control plot, and the second will save that picture actually. So now we want another one for temperature global also. Instead we can just stay for temperature local and add an animation for sorry, execute command for O2 local mole fractions. So let's go for oxygen. So we will create, edit a new one, new, and this we can make O2 mole local after every 50 iteration, and we will define a macro again, and this macro will say macro O2 mole local. So okay, and now we'll start saving it in the macro, and again start from here in the display, in the outline view, O2 mole fraction local. We'll go to the draw mesh, display, close, display. Yes, Now it is displaying correctly. Just check and close and end macro. Now this macro has been defined using the GUI, and we want to give it as the command macro o2 mol local. And okay, to check if it is working, the macro is working properly, we can check if the macro is working properly. So we will display any other thing, and now again give the command macro o2 mol local. You see the macro is working perfectly, so it will work in this also, but we need now again to save the picture. So we'll copy this save pic. We'll add a command over here, new command, we'll call it save pic2. No, or save pic after every 50 iterations, and give the same command as before. So the command is actually display save picture and the file name, and this is o2 mol fraction. Okay, and directly we'll give the percentage I dot jpg. Okay, now we have defined it and the execute manager. We execute commands also and automatically initialize and modify the case. So we're ready to run the case, so we can directly click the continue calculate button. It will take quite some time, and probably will ask whether to rewrite the report file, because we already did the simulation once and the report file was already written once, and now in this analysis it will rewrite the report file. Yes, click to overwrite. So here it asks to okay to overwrite, and the main thing is original settings. Yes, yes. And now it will, once this has started, the iterations have started, now it will keep running, and after every 50 iterations it will keep changing the conditions and continue to solve it. To check if the condition is perfectly executed or not, so we can go to the voltage setting, and now we'll check what voltage it is plotting. Yeah, it is well above 1.1 volt. That means it is originally at the same the original setting that we defined earlier. It is operating at the same condition, but the temperatures current on taps, yeah, it should be like this: minimum utilization action. Yeah, because this solution was already converged previously, so there it is already at exponent -5, so it's already converged solution. I'll stop the video over here, and then we'll see when there's a change in the there's a change in the modification that appears after 50 iterations. Now as you can see, the first iteration was almost completed, and now it is automatically plotting all the pictures and saving them. So here I would like to show that when we save it by the animation, so the animation, there is no, we cannot draw the mesh, but when we save it using the execute commands, we can save the mesh also. We can draw the mesh. So we'll go into the Fluent folder, and now all the pictures are being saved over here. So for the first iteration results, for the first iteration, you can see the H2 mole fraction. H2 is only being plotted using the animation tool. So if we go to the, we plotted this earlier, and you see the H2 mole fraction in local condition and the O2 mole fraction local, O2 mole fraction in global. But you see the local one, now this is being actually saved through the execute command. You see, because there was the option to draw the mesh, but when we go to O2 mole fraction global, you don't have that option. Temperature in global, temperature in local, and now this is the temperature in local using the execute command. So now it has actually changed the condition, and how to check whether the condition is properly changed. So go to the voltage tab, and you see the voltage actually dropped to 1 volt. So the condition has been changed properly, and it's continuing to solve it. Like this, it will change all the modifications, save the pictures, and this saves us the work to every time change the conditions manually. So this session, we will conclude this session at this point, and it will continue to solve it, and in the next session we will go towards the post processing of these results. Thank you.